Good. Any questions? How's the whole Blackboard submission thing working? Everyone seems to be getting it done, so that's good. Well, Frank, you're challenged. Like we're not all challenged, right? Yeah. All right, so I did get some scales. It's kind of fun. I only got a few metrics. They're the metal ones. So if you don't have a scale yet, I want you to grab one out of this box. So I would not grab the metal one, but grab these like white ones, right? Anybody need one? Yeah, come get it. I want to play with them a little bit. I want to make sure. Huh?
Why not the metal one?
The metal are metric.
Oh, okay.
Yeah, and I'm not doing metric yet, but there are some metric ones in here. So if you didn't buy a metric, you can just borrow one if you need it for something. But I want to talk about it and make sure you know how to run it, because they're pretty handy for what we're doing right now. They're very handy. So remember, there's two different kinds. There is the architectural kind, which looks like this, which looks just like a tape measure. 1/2 inch, 1/4 inch, 1/8 inch, 16, right? It goes down to 16. So if you see that, then you've got an architectural, and the scales are going to be kind of different. The scales are going to be like, this is a 16 scale, which means the 1 is broken into 16 different spaces, right? So then we could look at a 1/2 scale, and that just means that the 1 inch is half of, right? But I'm going to focus on the engineering scale. So the engineering scale, it has a 10. So for full scale or 1-to-1 real size, there are 10 increments for every inch, right? So if you're looking for, like, I want to draw 1-to-1 with this crazy scale, you're looking for the 10 scale, which means an inch is broken into 10 spaces, a 1/10, right? So this is a 1/10, this is 2/10, 3/10, 4/10, right? 5/10. 5/10 is a 1/2 inch. All right. Now, going back and forth, if you have like on a drawing or you're given information in fractions, like a 1/4 inch, you got to use your calculator. If you don't know the decimal equivalent to a 1/4, you got to take your calculator and go 1 divided by 4, and that's 0.25, right? So where's 0.25? Here's 0.2, and there's 0.25, and it's about all you can do if you're manually trying to lay something out, right? What's nice is we can lay this on a drawing, or actually we can lay it on an object sometimes and actually do some measuring to get some idea, right? Now, let's figure out how the scales work. So what I'm going to do, and you can do this too if you want. Oh, come on, you can do this. Focus. Is I'm going to draw a 4-inch line, 1-to-1. Four-inch. And the scale is 1-to-1. That's how we write the scale typically. Sometimes you'll see it 1-to-1 where they actually write it out. It's not very common. Sometimes I have seen this, which does not look good. That's not like, it's not great. It does work. Like you could go 1-to-1 with this slash, but I wouldn't do it. This is probably the preferred. And it's going to be in the title block, and the title block, that little box is going to say scale, right? So it's pretty straightforward. All right. So then if I take the 20 scale, and this is how this scale works, is you always use the real number. So if I want to draw a 4-inch line at 20 scale, which is a 1/2, that means there's 20 increments for every inch. That makes sense? 20 increments for every inch, and you can see they're getting pretty small already. But if I'm going to draw the 20 scale and I want a 4-inch line, then I literally just read the scale and go to the 4. right? And I'm reading that 4. And this little 20 is just reminding me that I'm on the 20 scale. All right. And on the drawing, it would be labeled 4 inches. And this would be a 1 to 2 scale. Half scale. It's half as big as the first line I drew. Make sense? What's nice about these is you don't have to do any math. You just read the scale directly and draw. That's what's nice about it, right? If I wanted 10 inches at 20 scale, I go to the 20 scale and I find the 10 and I mark it. Boom. I just have to know what scale I'm working with and use that scale over and over. All right, it goes up to 30. So now I have to find the 30 scale. And I'm going to draw my 4-inch line. On the drawing, it's always 4 inches. That's a 1 to 3. But if I was going to dimension it on the paper, it's 4 inches. We always put down what it really is. Yeah? That's how they work. And you get 6 of them. You get 6 times reduction with this tool. If it's beyond that, take this little tool and set it aside because it doesn't work for 1 to 10. Yep, use that directly. Yep. Hey, I don't give you all the information up front. If I did that, we'd be done in a week and you'd be buried. We'd just dig you a pit and put you in it. All right, yep, we're just gonna do them all. So you can just do them all. Here is 1 to 4 or 40 scale. Here is the 50 scale, which my eyes can just barely see the little ones. And then there's the 60 scale. And I gotta find the 4, which is pretty easy to find. Yep. Right, so I'm 1 to 3, 1 to 4, 1 to 5, and I am 1 to 6. And these are all 4 inches. So 6 times reduction is pretty good. Like the tool does pretty well for that kind of thing. So once you figure out your reduction, you can use this, go for it. Just make sure you lay down the correct. There's not a lot of difference between the 5 and the 6. So if you lay the wrong scale down and work for a few minutes, then you just really muck things up. So questions on the scale? It's handy, right? The architect one is the same way. It's just a little, I think, more difficult to figure out. So the 16 scale, that's a normal one, right? Then there's all these versions of it. Like here's a 3/4 scale, right? So there's 1 inch, there's 2 inches, there's 3 inches. If I want 3 point something, 3 1/8 or something, then I have to like go this direction with it. 3 1/8, 3 1/2. So it's a little different to figure out, right? Architects are a little different. It's 3/4 reduction. So that's 3/4 of an inch equals 1 inch. So that's the reduction, right? And there's other reductions. There's 3/32. That's a really pretty small one. So, and then there is an 1/8. So that is like if I wanted to draw the 4-inch line at an 1/8 scale, it's right there. From there to there, right? If I wanted to draw 4 1/2, I got to move this way and pick up that little half to right there. So it's weird. Anything over an inch, you got to look back at this part and come up with a little fractional piece. And that's just so they didn't have to put all those little lines on there. But once you kind of get used to it, it's like, oh, okay, I get it, right? So there's that. And then the metric one is similar to the engineering one. So that one, you can figure it out pretty easy. So here is 1 to 100, 1 to 50, 1 to 20. So any of those scales you can get. And they actually show you the scale, right? 1 to 25. One to 20, and that's the reduction. So that's 50 millimeters. So this whole thing's in millimeters, although I did see somewhere where they had it in like meters. Oh yeah, right here, meters. So that's a 1 to 100 reduction. That's a lot. Where 1 meter is right here, or 1,000 millimeters. It's like, whew, that is reducing. 1 meter is right there, right? 1 meter is 3 feet. That's big. So that's a serious reduction. So 1 to 100, that's 1,000 millimeters right there. So each one of these would be 100 millimeters, right? Because it would be 10 times 100 to get to 1,000. Yeah. I mean, it takes your brain a second to like, whoa, figure this out. But not too bad. So then you have the ability, especially with the metric system, since it's just factors of 10, like you can adjust that scale however you want, right? So if you said this was a millimeter, then that's some kind of increase, right? That's like a 10 times, because I'm guessing that's a millimeter. So just change the scale in your head and now you're blowing something up instead of reducing it. That makes sense? This becomes 1 millimeter, then that's 2 millimeters. Well, that's 10 times bigger than what the object actually is. If you were drawing something really small, you need to make it bigger. These are not as good at that, although you can do the same thing. You can say, okay, I'm going to use this 10 scale, but that's going to be a foot. So that's a reduction, right? Or I could say, okay, that's going to be a foot. So now I have a really big scale. So you can create your own kind of scale with this whole 10 factors of 10, which is what this is. The architecture one, you just can't do that stuff with it. It just doesn't make too much sense. So, all right, good on the scale. Hopefully you'll be able to use that on this last assignment. And then you'll have other projects in this class. Like we do a project, and guess what? I make you do graphics on your project. So you'll be drawing more. You'll be using these skills through the term. But after this, we jump into Excel for a while and figure out how to make equations in Excel and make them work for us. But sometimes I make you like make a drawing and then bring that into Excel. That's kind of an engineering package as far as how we would use Excel. So if you know Excel, big bonus, that's good. It'll probably go well. But if you've never done formulas before in Excel, then that'll be a new challenge for you. And then if you've never displayed formulas in Excel, that's the hard part with Excel is you can make formulas all you want and make them all work super cool. But if you're going to share that document with other engineers, they're going to want to see the formula that you're using. They don't want to go in and have to figure it out. Like, what is are you using bending stress formula? Are you using shear strain formula? Are you using Young's modulus? What are you using, right? You can't just have a bunch of numbers and say that's right. So we have to be able to show it. So when we get in Excel, we do some pretty unique things. All right, let's talk about a little more graphics. Y'all can see that? Yeah? All right, so we're going to talk about dimensioning. This is not my PowerPoint. Yeah, I wouldn't do this stuff. Yeah, no, that's just unnecessary stuff. So when we're dimensioning, I'll try to follow this thing. We are looking for our goal when we're dimensioning is full shape description. We have to have the full shape described. Everything needed to send it off to somebody to make it. And we're really hoping nothing's missing, which is a very difficult task if you have any kind of a complicated object. To get it all on there is really pretty hard to do. So that's the full thing is we want full size and shape description with our dimensions. We want everything located. So if there's a hole, it's got to be located. And that's usually not just in the X direction, but also in the Y direction. We are two-dimensional like what you've been doing, right? We took a three-dimensional object and we put it down two-dimensionally, right? Front, top, side view. Now we have to like position everything. The dimensions you're given, if you are working off a drawing like this, are typically not done correctly on purpose. And that's so you don't just regurgitate what you're given. Like, oh, I'll just dimension it like that. That would be way wrong. Okay, so we want to try and learn as many dimensioning standards as possible quickly, but definitely we're not going to learn all of them. That's just not what's going to happen. If there's a tolerance, we would include the tolerance. What's a tolerance? Anyone know what a tolerance is?
The highest and the lowest point of your nominal.
Let's say I have a 4-inch length and I wanted to dimension that. What would the tolerance be? Any ideas? Like what it means?
Depends on what you ask for.
It does depend on what you want, but the tolerance would be the allowable variation to the 4 inches, right? So if you're sending the 4 inches to a chainsaw dude who's making stuff with a chainsaw, right? It might be plus or minus 1 inch, right? If I'm sending it to machinists, it might be a thousandths. 4 inches can be 4.005, I'll say 5 thousandths, right? It can grow that much, or it could be 3.995. It could be less 5 thousandths. So it's the amount, the variable amount.
The range. Works the same like independent stuff.
Yeah, absolutely. Yep. Yep. So if you go to work for a company that is manufacturing something, you will typically be involved with tolerances. Like if we're making something that's just not important, but I'm dimensioning at 10 thousandths, whoever gets it doesn't know that that's not important. Like they would look at that and go, holy shit, I got to hold this to 10 thousandths. You just drove the price crazy up because it's very hard to hold things to that kind of tight tolerances, right? A lot of drawings are just going to have a general tolerance note. In other words, we don't put the tolerance on every dimension, but there's just a general note that says plus or minus 2 thousandths or 25 thousandths or 50 thousandths, right? So we don't have to tolerance everything, but then there's other pieces that need to be kind of high precision and you're going to see a tolerance. So if there is a tolerance that is important, we would include it. And you might see some on some of the drawings. I don't think I went there yet with anything that I'm going to have you do, but just know that those things can pop up and we will cover different tolerances and how they look. All right. What was the last part? Okay. Oh no, is it going to do it again? I can't handle this. The top thing's super important. So I'm going to cover a lot of rules, but you can break those rules if it's in the sense of clarity. Like if it makes it more clear to put a dimension on the object, which is a rule we don't want to do. We don't want dimensions on the object. We want them off of the object, right? So if I look at this, most of these dimensions are off the object. There is a few that are like directly on it, like the 13, this 16, that number, right? We want them off the object. We want the object to kind of stand on its own and not have a bunch of junk in it. So that's hard to do on a complicated objects. Sometimes we have to put a dimension in there. So if it's for clarity, you can break a rule. I'm just telling you that right now. There's no other way to do it. And it's just going to be a mess to get it off the object. You can put it on the object. Even though the rule is no dimensions on the object. Okay. So we want to dimension each feature once. We don't want redundant dimension. So we don't want to dimension something in the top view and then dimension that same dang thing in the front view. We don't want to do that. All right. So don't double dimension.
But when you have a whole right, a whole diameter, it's the same.
Yeah, absolutely. So we'll kind of get into that. Yeah, there's some examples here. But the last thing is we want that dimension. So like on this one, Remember this one? We kind of did it as a practice thing, right? So the overall dimension, this profile is the most descriptive view. It should have the most dimensions on it. Because it's pretty clear, you know, like this dimension should be here and not over here in the right side view where it shows up as a hidden line, right? We cannot dimension to hidden lines, first of all, but you want it in the most descriptive view. So if the overall dimension is best here, this is where it should go. If the location of this edge here is nicely viewed here, that's where it should go, not up here where like this, that may be a solid line up here, but this is a better spot for that dimension because it's more descriptive. All right, so try to put them in the most descriptive area. I'm going to talk a lot about this, so if you want to take a note, you could. All right, clarity, we did that. So here's just an example of how busy it can get. And several rules get broken here, right? We have dimensioning on the object, like right here. Now, could this have gotten pulled out up into here? I think probably so. So that's really not a great spot for it. There was room right in here to pull that out. So if you can get it out, because I'm going to look and see, oh, yeah, no, they couldn't get it out. Or, oh, yeah, there's a perfect spot to get it out. Why didn't they do that? Right? Leaders are really handy. Like these are called leaders, right? And you can sneak them in all kinds of places. R would stand for radius. Yeah. So the important thing with leaders is they're never vertical and horizontal. That gets confusing with the part. They always go in at some angle. We always shoot them in at some angle. Even if it's just a slight angle like the 73 up here, it's getting pretty vertical, but it's not vertical. It's at an angle, right? If, 1 second more on leaders, the important thing on leaders is if they point to something, for example, let me blow this up a little. If they point to something like this, that's perfectly legit. Notice it touches, the arrowhead touches it. That's important. We don't just like point from a distance with a gap, right? And if the leader continued, it would go through the center. Does that make sense? So if this leader continued, it would go through the center mark. So in other words, we don't come down and point to like an edge of a curve. We just go like where we would go directly to the center, but stop it at the object. And they can flip around, like they can be like this, that's perfectly legit. Or they can be like this. That's fine too. However, some reason this person thought that was better than just pointing to it and stopping it here. I don't know about that. That's personal dimensioning preference. I'm not going to grade you on that. What I'd look for is that, hey, does that thing shoot through the center? Because that's what we want. Frank, you had a question. Oh, yes. Juan, you had a question. I answered it. Such a good lecture. What's the 2 times mean? Means 2 locations, and it is very obvious at the 2 locations. That's the only time you can use it. Is if it's so obvious, like there's in this view, there is only 2 holes. So that's perfect. I saw one up here that I thought was, oh, this is a different one. Oh, that's pretty obvious, right? 5 locations for this thing. 1, 2, 3, 4, 5. Whoops. What? 6 locations. Okay. That's better. Don't get your locations wrong. So that's good. I mean, that saves you a lot of dimensioning, right? So these fillets, like they're all different, so they're all labeled and called out. A lot of times they're the same. So you can just call out R5, all fillets, right? So use that strategy and don't be afraid to use words to explain things. Like it's okay. There's a lot going on here. We're not going to learn everything, but all these symbols, that's all part of dimensioning. In our book, you could look up all those things like this U thing. What's that mean? That's a bore. It's a boring process. There's I think some depth on here. I thought I saw an arrow and a depth. Here's a chamfer. Right? So a chamfer is just not a rounded corner like this, but just a straight corner, like it just chopped off. A lot of times they're at 45 degrees. This one's super hard to see because it's so small. 28 chamfer. So sharp edges, really sharp corners, very high stress locations on parts that get loaded, and most parts get loaded, right? So we like to take those very sharp corners and just round them off with a radius or a chamfer. That'll drop the stress considerably. And when you take strength of materials, we talk about that a lot, and we do both those calculations, and you'll see it. So let's look at their dimensioning. Looks pretty good. Not much on here. I don't know why they put that on there. I would pull that off for sure. No reason for that to be in there. There's lots of space. So this is the same kind of thing. This dimensioning, I think it's actually an example, not a project a student would do. So, some of it I don't quite get. Doesn't all follow the standard, but most of it's pretty good. These are called dimension lines. I think I said this once before in this class. Why? Because it holds the dimension. And this is important because this is the lingo we'll talk about. I'll be like, your extension lines, they're terrible, or your dimension line is wrong. It can't do that, right? You got to know what I'm talking about, or what somebody else is talking about. So these are dimension lines. What's that? It's a dimension, but it's also a tolerance. Yeah. So that means, hey, it can be 11354 to 11351. That's the target. It can be, that dimension can be anywhere in there. Right? And that's important for the person building it. Very important. So they know they're going to aim for, so not sure what that is. Those are, oh, it's a diameter. Yeah, so they're going to aim for the smaller side on a diameter like that, right? Because it's easier to remove material than it is to like put it in. You can't put it in. So if they go over the 5.4, this part is scrapped. If they go under the 5.1, they can go a little more and maybe get closer to 5.1 and go a little more, and boom, they got to 5.1. So on holes or things that remove material, they were going to aim for the smaller side. On outside dimensions, like if there was a tolerance here, they would aim for the bigger side of 64, right? Because then if they miss it on the big side, then they can take a little more off to get closer to 64. So that's called maximum material condition. When we do tolerancing, we have to think about like, oh, where are they aiming? And they'll probably come in closer to that target than hit just the broad range. So that's important for us if parts are mating. If parts are coming together, we need to know these tolerances are going to work. If they miss one side on one part and they miss the other side on the other part, will it still function? That's kind of our job. All right.
Question.
Yeah.
Are we covering the GD&T on this class?
You just get it introduced.
Okay.
Yep. So you'll understand the concept of GD&T, and then we'll go through a few of the basic ones, what they mean. Yep. Good. But you can see it gets super busy. And in the end, really, we want to be able to read this. We want to understand oh, what is this view JJ? And where's it come from, right? So this is some kind of right side view. It's to the right of the front view. We know that much, right? And it's referring to this JJ cut. And here's J, and here's J. So that's a cut that goes right down through here. We peel it open and we set it here. Right? It's called an auxiliary view or a section view where you cut it and set it. So it's not a standard right side view. I know that because it doesn't say right side view. It's not. And this doesn't say left side view. It's not. It's a cut. So they're slicing it so we can see the internal pieces of what's going on. Because if you just drew the left side view, it'd be a mess of hidden lines, just chaos. Yeah.
I don't see a same front view.
I don't either. Right here? Right here? Nothing. Didn't name the view at all. It's bad. It's just bad practice. Why not? You're labeling all these other views. Why not label that? So, I mean, I'm sure an engineer would say it's obvious. It's obvious that this is the front and that this is what? The bottom? That's my assumption.
Most of the prints nowadays, they are not labeled.
Yeah, no, that it's kind of a lost thing. But I don't like making the assumption that that's, because everything's not in projection, like this is not in projection. So. Anyway, you can see, and we have a lot of different views. We're not even gonna cover near all of the possible views that you'll come across, but. This is some kind of a blown up view, right? So it's section LL and it's double size. So and then I have to find section LL. So here's one L and here's the other arrow. See that little arrow right there? It's just pulling out a very small piece right here. And then putting it up there and blowing it up. Okay? So all strategies to try and full shape description. That's our goal. All right. So a dimension has the numerical value defining the size, shape, location, surface, texture, blah, 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 right? Typically, text is 1/8 of an inch in your dimension. Okay, so that's what we want to put down when we do it. Line spacing, that can be, when they say line spacing, they're talking about the spacing between the dimension line and the text. So see that little gap? So this is the dimension line. It comes, it stops. We are going to do our text inside the dimension line. So it comes, it stops. It's a 1/16 kind of gap. Just make it close, but not too tight. Okay. Notice how this one's offset. That's good strategy to get it out of the way of this extension line. This is actually a rule. Extension lines are not supposed to go through dimension lines. That's a no-no. But they must have thought there was no other way to pull that thing through. So they just did it. So we want to try to avoid extension lines or leaders blowing through dimension lines. Yeah.
Is there ever an instance where like that's just too busy, so you just do like a second page for the next view and then?
Yeah, definitely things like that happen. And this is super busy, but it's really hard to put views together in your head when they're on separate pages. This is a lot easier, believe it or not. I mean, this is all like maybe just this on this page. These are just projections off of this, so that all that could be on a different page. Yeah. Yep. Very possible. This is a super complicated thing to try and draw. So. We're going to use decimal inches when we put our numbers down. You don't have to put the little inch symbol down. If there's a note in the title block that says dimensions in inches, right? So that's what we want, is we want just to put that in the title block, and then we don't have to use the little two marks for inches, right? We're not going to use feet, and it's just, the assumption is it's all inches. But it needs to be in the title block. If it's millimeters, that needs to be in the title block. All right. That's the note. It's all good. Dual dimensions, we're not going to get involved in that. Yep, not doing it. All right, so let's just talk about some basic dimensioning. So here's the note down here. All decimal dimensions should be held to. That's a basic tolerance, right? So usually that would be in the title block. If I don't give you a tolerance, then don't worry about it. You don't have to put it in, because we're not really going to go there yet. But if I look at the dimensioning of this, just example dimensioning, this is good, right? This is all good. This, you have to decide whether you need that in there or not. Okay. If it's symmetrical, if you leave it off, then people could wonder, oh, what's that dimension? Should I make the assumption it's symmetrical, right? So this one is put in, and it's just put in black. just so we talk about it. If you note the object is symmetrical, then this center line really should go all the way through. That is a standard for symmetry. If a center line goes completely through the object, it's symmetrical. But you could also write on that center line, symmetrical. Then the question's answered, yeah.
And manufacturing, that note right there, the 1 thou note.
Yeah.
Question engineer, okay, do you want 1 thou overall? or
Yep.
1 thou wrench?
Yep. Exactly. You want, is it plus or minus?
Yes.
Right. Is it just plus 1,000s? Meaning it can just grow bigger than all these dimensions? Yeah. Exactly. Organization is good, right? We have the overall dimension down here. This should touch. This is bad. This is good, right? Arrowheads should touch extension lines. These are extension lines. Extension lines never break unless they're a center line. So this is an extension line, but it is a center line. So then it should be a short and a long. That's a center line, right? But most extension lines are just solid lines. They travel to whatever they're marking, and then a gap is left. Right? The gap is typically the text height, 1/8 of an inch. You can get it a little closer, a little further, but you definitely don't want it like an inch away from whatever you're marking. It travels to what you're marking. So this travels to it, this travels to it. Extension lines. They don't break. They can go right through each other. No problem. We really don't want them to go through the dimension line. But this is perfect. 2 extension lines crossing happens all the time. Sneak in your leaders. I don't know why this 15 is way the hell out here, right? I would have brought this 15 down and put it in line with the 30. There's no reason for it to be yarded out here. So kind of keep it compact around your object. Don't try and spread it out, right? You want to keep it tight. But the distance away from the object should be consistent. And there's a standard for it. I think it's 3/8 of an inch. I'm not gonna measure your distance away, but I'm gonna look and all the way around it and go, yeah, it's consistent all the way around.
I asked that question once to an engineer. Why? I mean, the hole was way
It was way out there.
Yeah.
Yeah.
And I said, when I do copies of the print, sometimes it doesn't come out.
Yeah, I know. Yeah. It's laziness. That's what it is.
Yeah, his answer was because, he wants that dimension to be, not separate, but to call the attention of the manufacturer.
Yeah, well, if it doesn't show up on the print, it's a problem.
Yeah, and that's one of the problems is that when
Yeah.
you do copies,
So the standard is 3/8 to the first dimension. And then if you're stacking, this is stacking, it's 1/4 and 1/4. Quarter's kind of tight for me. I kind of go 3/8, 3/8, 3/8. But as long as it's consistent and doesn't get too far away from there, you're gonna run out of space. So you're gonna keep yours pretty tight. At least you should. Notice that the smaller dimensions go on first, and then the next one, and then the biggest one last. And that's so your extension lines don't cross your dimension line. Just kind of. Yeah. No, but you want it to follow some kind of standard, so they look at it and go, oh yeah, I kind of get that, right? So here's everything called out. This is a location dimension. The 20 is locating the hole, right? The 30 is locating the hole. Where you pull it from is up to you, unless there's something called a baseline for the part. So that's kind of next level dimensioning, but this is weird that you would pull from this side to get the 30 and from the bottom to get the 20. That's kind of odd. Well, it depends on where the important features of the part are. But if you're just gonna do it, like, I would keep it together, like the 20 would be here. And this 30, I wouldn't put it there, I'd put it over here. So X and Y are relatively close to the location for this. Right? Just so they're kind of in the same proximity. If we don't know a baseline and we don't care where we're pulling from, which is the way we're going to operate, then cluster them, get them kind of close to each other. So the individual doesn't have to like do higher level math to figure out exactly where this hole is, right? It looks like it's right in the middle. This is 60, that's 30, this is 20. I don't know if it's symmetrical. I'm gonna assume it is, right? So, yeah. So, yeah. Visible gap, extension line, dimension line. These are the sizes of all things. Good? That's enough. Just use kind of that practice to do this next exercise. The object is simple, which I expect everyone to get the front top side correct. And then you're going to spend your energy trying to figure out the best way to dimension it, right? And we don't want to leave anything off. We want to know the size and shape of the entire object. I don't know what else is in here. Yeah. Those are different ways you can get a dimension in. Don't jam it. Like, we want our dimensions to look like this, but if there's just not enough room, you are not allowed to, like, sometimes somebody will make their text like a 16. No, right? We need 1/8 inch text throughout the drawing. We can't make it smaller just to squeeze it in. Arrowheads, there's a standard for that, believe it or not. So like the arrowhead standard, and people, if you haven't done arrowheads, like people struggle with this. They're normally 3 times the text height. So in length, which is going to feel kind of big, right? So if I'm 1/8, oh no, sorry. If I'm 1/8 text, that's from here to here. So that means my arrowhead is the same length as your text. So that's about the right size, right? I don't know what I was marking there. I wasn't marking anything. So here, I'll put an extension line down here. Pull this off, and then I'll put in a dimension of some kind. Leave some space, right? So there's my dimension that I'm pulling off. So if I have 1/8 inch text, that's about that tall, then the arrowhead typically is that long. You just pull it out and make it super skinny, and it's super easy to fill in. It's about all you want for an arrowhead. Doing it manual, right? So they don't need to be like that. And then you gotta like, oh, spend an hour and get a bunch of graphite on your drawing and just make a mess, right? So not like that. Just find your spot. I'll do another line, right? And just pull it out, just a little. They're super skinny and tiny, and they just kind of mark a spot and they touch. Okay, all text, unless you're using grid paper, which you're not. Even if you just have to do it by hand, like I just did, give yourself a guideline. I don't even care if you measure it's an 1/8. It's approximately an 1/8. That's all I care. And if it's all that size, that's all I care. Right? But it does help you like keep some decent text. It's time consuming. Takes a while. All right. That's good enough for that. Let's talk about title blocks real quick. I loaded up out of the book A size title blocks and B size title blocks. You're going to do B size. That's big paper. 11 by 17. So it gives you more room, right? So this is how the 11 by 17, I think I said form 4. That's this one. So you'll see that it's 16 inches. That means it goes on the long side of the paper. Right? 16 inches is not going to fit on the 11 inch side. So that means it's landscape position. So the first thing you should do is 16 inches. I think this is 17. So that's a 1/2 inch in, right? A 1/2 inch in. Make yourself a border. Make yourself that title block down at the bottom. Just do that first, because then that sets up your drawing space. Does that make sense? Yeah. And then the rest is here for you you know, 125, 388, 388. This looks like 1/8 inch text, 2 inches, and 0.62, 5/8 tall. Piece of cake, just put it down. You can fill it in later. I wouldn't fill it in first, but I would definitely lightly put it in. If you fill it in first, that just lays a lot of graphite on the paper and then you're dragging your hand over it the entire time you're drawing. It just becomes a mess. But you want to account for that space first before you start laying out your views. Lay out your views, pick a scale that's going to allow you to dimension around it. Don't go too big, don't go tiny, or I'm going to go, why is it so small? So it's your job to figure out like, oh, how big can I get it and still comfortably get dimensions around it? Okay, so that's in there. I can print a few of those off if we need them. Trying to think of what else. I think that's it. You probably want, I could show you the exercise. It's out of that same group as we had before. It's this thing, and it's number 7. And I think the tick marks are 6 inches each. So I tried to make it big enough, like, okay, 1, 2, 3, 4, 5, 6, 7. It's 42 inches in the front view. So that's definitely not going to fit on the paper. So that would make you scale it. Cool. Half scale would be down to 20 some. I'm not going to work. 3 scale, 4 scale. You'll figure it out. But figure it out before you start drawing or you'll be in trouble. All right, questions. This one will take a while. I think I gave you till the 20th. So today's the 17th. Good. All right, paper's there if you want some. If you want to take one of these home, if you don't think you're going to get it done in here, go for it. I wrote MHCC on them all. We are doing number 7 on B-size paper. Yep. Front, top, side view, I think it says. Yeah, it says instrument draw. Oh, bad spelling. Front, top, and side views. Number 7, B-size paper. Form 4 title block. Each tick is 6 inches. Scale is necessary. Dimension completely. And I should have put 1/8 inch text. So I'll correct those little arrows. All right, there we go. Good to go. We're now in lab time. Yeah. Yep. Number 7, right? Number 7. Space. Pick each tick. Yes, each tick is a technical term. 6 inches. Yep. Yep. That's the start, right? Yeah. Figure out your scale. So how big is this thing in real and how small is it gotta get to get on that paper? Good times. I will print off the title blocks if you'd like one. I'll make a few of those. Okay. Printing's always super fun. Lots of applications. See if it works. So if you wanna be that engineering student carrying around a T-square, you can take that one too. So cool. Absolutely. Hang off your belt. Did you have a board at the house? Like a drafting table? Wow, that's so cool. It's electric or manual? No. But it can go up and down and tilt? Oh, dude. It's like, used to be my yoga. Sit at a drafting table. I'm not doing calculus, I'm not doing physics, I'm sitting at a drafting table. It was awesome. I used to love it. Cause I dreaded calculus.
Side jobs, like side,
Yeah,
side money.
yeah.
Like built their shop. Watch him, I just sit up there and watch him do drafting. Yeah, there we go. So fun, all the good stuff.
Has an arm? Dude, that's priceless. They don't make them anymore, man.
No.
You can't find them. Title blocks are up here if you want one. They're great office tables too. Like, we
Yeah.
tried to get some. We used to have a room full when I first started here. And then they got rid of them all. I want one in my office. My office was too small.
People together, like, you know,
Oh, I'm
they
sure
got
you
enough
can.
Parks that you.
Yeah, yeah, that's right. I think that'd be a great capstone project, is to build a drafting table with the arm. That'd be so fun.
So I can do this at home, right?
Yeah, that's the
Okay.
thing.
Yeah.
Like, if you didn't, oh, I didn't stop the recording. If you weren't here, right, Frank, you just have to come and get this recording, watch it,